Hi, everyone. My name is Moody, and I'm a researcher at IFT. Maybe you are not familiar with IFT. IFT is the Institute of Free Technology. Under its umbrella, there are cool projects like Status, Logos, Waku, Codex, Nomos. We are an incubator project within the research identity of IFT. Our project is called Nescience. Today I will dive into what is Nescience. Just to be clear about it, it's like state separation architecture, so combining private state and public state, but also enabling selective privacy on the user side rather than the apps. So to start with the problem that we are trying to solve, nowadays we have public blockchains that are transparent by design, but they sacrifice privacy because they lack privacy. And then we have private blockchains that are private by design, but they sacrifice functionality and integration. So the problem is we want to solve how we can preserve the privacy without losing the benefits of the public blockchain. Without a hybrid approach, actually, users have a choice, either to go fully public, so they will get full functionalities, but they will have no privacy, and they can have private blockchains where they have privacy, but it's limited. There are some workarounds about this, like mixers or cross-chain bridges, but these can be a little bit problematic, and sometimes they break composability. So what we need is an architecture that can combine public and private transactions that can work together under the same platform. So what we are trying to do is to combine public state and private state together. So what is Nescience? Nescience, we call it NSSA. Maybe the name is not the best, but it's like Nescience State Separation Architecture. And it enables selective privacy. I will go through selective privacy later. The pronunciation is Nescience. So Nescience actually means lack of knowledge. So our idea is that instead of having privacy set and fixed by dApps and developers, we want to let developers and users to choose when transactions are private, when transactions are public, and how. So the main idea is to have a double-state architecture, account-based model, and UTXO-based model that can be like bridging between transparency and shielded environments as needed by the users. So what we'll have is a public state. It's an account-based ledger where we have accounts and balances, and a private state that is a UTXO-based where it represents the ownership of data or sets. So what we are trying to enable here is, let's say that Alice wants to send some transactions to Bob in a shielded or deshielded way. I will go through these definitions later. But it will allow Alice to create a UTXO, a new UTXO for Bob, and send it privately. So what we'll have is selective privacy within execution types. So we will be having 4 execution types: public execution, private execution, shielded, and deshielded execution. So public execution is transparent execution. We only need a VM. We write and read from the public state. We have a private execution where we use a ZK VM, and it reads and writes from the private state. Then we have shielded and deshielded execution. So shielded execution, actually, it reads from the public state and writes in the private state. So we are spending publicly, but who is receiving funds or assets or data privately. And in deshielded executions, we are writing from the private state, we are reading from the private state and writing in the public state, meaning that users can spend their funds privately, but they can receive them publicly. And here I want to give an example about shielded execution and de-shielded execution. So in shielded execution, imagine Alice willing to send some funds to Bob. So what she will do is there will be a ZK proof that needs to show two things: that Alice have these funds on her public account, and that the new private node that Alice will build is correctly formed. In the de-shielded execution, Bob have a private node of these tokens that originally maybe received from Alice, and now he needs to de-shield them. So what he needs to do is he needs to move these tokens from his private account to his public account. So the transaction will provide a proof that this token is valid and is worth this value. And Bob is allowed to spend it, actually. So it will be destroyed, nullified. And then the tokens will be added to Bob's public state. So why selective privacy? So in our view, selective privacy addresses real-world needs. It shifts from being fully public or fully private. It also somehow solves the problem of privacy leakage in account-based model, where, for example, if you think about a donating platform, the donor is somehow maybe hiding his ID, but in account-based model, we can still leak some patterns. To solve this, actually, UTXO models break this linkability. So whenever users interact with a contract or send a transaction in Nescience, think about it as having a privacy dial that you can set. So at the moment you craft a transaction, you can choose if you want to have a public transaction, private transaction, shielded or de-shielded execution. So you can think about it as when you send an email, if you want to CC everyone, so you go public, or you want to send private email to some people. So yeah, this is how we see things. This is how we want to shift this choice to be from the user, choosing whenever to be transparent or private, rather than the DApp or the developers that dictate the level of privacy of users' transaction. So here I will just show you an example about how the architecture is made. So for public executions, we don't have a ZK VM. So we have the user that will have his public state, public input. They will go through the sequencer. They will be rerun, and the public state will be updated whenever there is a transaction. Same for private execution, but as you can see, we have a ZK VM. We have the user that is compiling his private data into a proof. There is the ZK VM that will verify this proof, and the private state will be updated later. Shielded executions, actually, as I said, we are going from public to private. So you need to think about sending some tokens publicly. So let's say that you need to send 50 tokens. What you will do is that you will submit to the VM the request of spending 50 tokens. It will be verified that you have these tokens, and your balance will decrease. At the same time, the user will be sending private calls to the ZK VM, saying, OK, I want to send, they are proof, but within the proofs, you will have like, I want to send 10 tokens to user A, 10 tokens to user B, 10 tokens to user C, etc. And no one will see this. So everyone on the chain will see that I spent 50 tokens because my public balance will be decreased, but no one will know how I spent them and to whom I sent them. In the de-shielded execution, actually, we are going from private to public. So what the user will do is whenever they decide to de-shield some tokens and update their public state, they will be doing this. So they will feed the ZK VM with the private inputs. And what will happen is that there will be some controls. We will see later a more clear example. And what we will see is that the receiver account balance will increase, but when we check the transaction, we won't be able to link where these funds come from. So this is an example of a shielded execution. So Alice wants to send assets to Bob privately. So she will initiate a public transaction, which is a shielded transfer. So the shielded transfer will lock Alice's assets publicly, and it will create a private UTXO for Bob. So on the public phase, Alice's transaction will run on the public VM. It will deduct its asset from the public account, and the output will be directed into a shielded pool. On the private output, actually, Alice will be building a new UTXO for Bob, and it will include generating a random commitment and assigning the ownership of this UTXO or node to Bob. So there is a ZK-VM that will be made, and this will show two things. It will show that the public transaction output value is equal to the UTXO value. So we will be able to say, OK, Alice wants to spend publicly 50 tokens. There is a proof on private proof that she will be spending these tokens. So the ZK-VM will only check this value. So we will check that what Alice wants to spend is equal to the node that she created. And it will tie this UTXO commitment to the transaction. So the sequencer, actually, what will do, he will execute the public part and decrease Alice's balance. And it will verify the ZK proof and update the state. So the public state will be updated through the public transaction, and the private UTXO commitment will be added to the tree of the UTXO. So like this, we have combined private and public execution within the same transaction. So what we are doing now? Now we are trying to work on hybrid smart contracts. So we want to build a logic under the same smart contract where public functions and private functions are touched, either like public state or private state within the same logic. So a contract can have a public method that triggers some private functions, or what we want is to be able to call from a private function a public function, like de-shielded and shielded executions. We also want to enforce that certain state variables can be only updated by private transactions or by public functions. So think about it like this. You want to deploy a smart contract in Nescience. So you'll have two facets, a public-facing part and a private logic part. For example, the contract might say, for public executions, maybe just do this state updates. And for private executions, we want the logic to happen on UTXOs. So the developer, instead of writing a smart contract for each execution, the developer would be able to write a unified smart contract where it can touch both public and private states. The logic will understand whenever there is a public transaction, for example, it will only touch the public output, it will only touch the public state. If there are some private functions, then the user will generate some proofs. They will be run through the ZK-VM under kernel circuits. Then this kernel circuit, so each private transaction or each private function will be seen as a kernel circuit. Then these circuits will be aggregated, and the user will be able to send the proof along with the transaction. So now I will just show a table on what are the differences between what we are doing and what is being done. We are not claiming that we are better. What we are claiming is that we are shifting the privacy towards the user. So we are building something that is user-driven rather than depth-driven. We are allowing 4 execution types, public, private, shielded, and de-shielded. We are working on smart contracts that can be fully hybrid. Regarding public transactions, we don't use ZK, so there is no cost for that. Nescience can be deployable as an L1 as well. We use Rust. We use RISC-0 ZKVM. So all the architecture itself is modular. Pieces, components can change under certain rules. But yeah, it's fully modular and fully flexible. So now the idea is that whatever we are doing, we are building public goods. We care about users. We don't care a lot about monetizing or making profit. And this is where the idea comes from. So I will just give some use cases where Nescience can be used. So often DAOs struggle with balancing between transparency and the voter privacy. So today, if we have on-chain voting, everyone can see how each address voted, and this can lead sometimes to some pressures or bribes. So with Nescience, we can build a DAO where proposals are published. So maybe it's like public, or the decision is public, or what we are voting for is public, but the votes are casted privately. And each vote can be seen as a UTXO note. Voters can submit their votes as private executions, so no one can see how they voted. What we will see is that the result is revealed, and we can also submit a proof that these votes were casted correctly. This is like, it preserves the voter anonymity and still ensure that the outcome is valid and it's transparent, and it's also encourage more honest voting, as there will be no fear of retaliation or no fear of pressure. Everything is seen as a secret ballots, all executed on a public blockchain. Another example can be private DeFi AMMs, where every swap is visible. Everyone can see who traded, which amount, and when. So this transparency actually sometimes leads to issues like front running, as bots can see a large trade and try to jump ahead, and can reveal maybe sometimes the strategy of big traders. If we use AMMs on top of Nescience, a user can perform these swaps in private, and the contract, the AMM contract, can just like accept these shielded or private swaps, where the proof is provided that every trade is obeying the rules. So like this, we can reduce the MEV because observers cannot pinpoint actually individual trades. And sometimes actually we could take a loan privately. So instead of showing what we are doing or like showing our financial situation, we can accept loans to be done privately between users and just show the total price change or the total amount. This is one of the last things that we care about. So sometimes when I'm talking to people, they say, oh, this is another Tornado Cash. Actually, it is not, even though I have nothing against Tornado Cash, but people are afraid about compliance. So one advantage of Nescience is users can choose when to be transparent. Imagine a business that wants to pay their salaries, so they want to use the blockchain for accountability, but they want to hide, they want to have some confidentiality, for example, hiding from suppliers or salaries. They don't want to show everyone salary. So what they will do, they can do all the everyday transaction privately, and they can use a viewing key. This viewing key actually allows auditors to check all the transactions that have been made. The only difference is that it's not being made all public. It's just giving the user the ability to choose when they want things to be public. So look at it as an opaque glass that is frosted when you are on private mode. Whenever you want to go public, transparent, you can show it. Otherwise, you can stay private, but you can choose who can see whatever there is in the glass. So this is how we see selective privacy. It's selective disclosure, and it gives user also privacy-preserving compliance. Thank you. Any questions? Yes.
Yeah, so I have like half a dozen questions.
Okay.
I will keep it short. Maybe just before, one first thing is, it's a bit counterintuitive, but you know, sometimes in terms of UX, constraining users is actually the good thing to do. And I'm thinking, for instance, if we think of the darknet markets, okay, they forced transition of the user from Bitcoin to Monero simply because trusting the user to do proper mixing on the Bitcoin blockchain proved to be unrealistic. Most were not doing proper mixing, and essentially they were putting in danger the whole system by their lack of privacy. So they kind of decided, okay, we're going to force you into a private by default coin, and now we know that privacy is preserved in our little system. So I guess my question is like, it's a bit similar to the Zcash problem, essentially, where if you have public and private cohabiting on the same network, and especially with state change transactions like those shielding and unshielding, how do you not weaken your anonymity set by the existence of those public transactions?
Okay, good question. Actually, what we care most about is, so we are not holding any data, any private data in the architecture. So users are generating their proofs on the user side. What we care about is just making sure that these proofs are valid. And these proofs, as I said in the example before, whatever value they have, they match the public value that have been requested originally by the user. So once we have this and we have this check, then everything should be okay. Whenever we see that, for example, the user is trying to send 50 tokens, but they don't have these 50 tokens, or the proof itself doesn't reflect these 50 tokens, then the sequencer will reject this, and it's not going to be processed. What we also encourage is with selective privacy, and we highlight this selective privacy, is that users can start using Nescience by being fully transparent. And while they learn about privacy, because privacy is not just hiding. We are not talking about hiding money or tokens, or it's about literally understanding what data should be kept private and how to use this privacy, when to disclosure, when to disclose this private information. So this is why we say that it has different type of things to do. What we care is the control of private and public data. And of course, if you want to do something that is somehow malicious, you are not going to use Nescience. You will go fully private and use some rollups or some mixers or Monero or stuff like that. So we don't put a lot of assumptions on the users because we want to drive the user to understand the privacy needs and why they need to use this architecture in order to achieve their goal. I don't know if I answered your question.
I'm not sure. So essentially, you're telling me that if I'm looking for very strong, absolutely resilient privacy,
sorry?
If I need some serious privacy where I'm thinking I need to protect myself against a state-funded actor or this kind of threat, this is not for Nescience.
Yeah. I mean, what I'm saying is that if you want to do malicious things, you are not gonna use this because controls are made in a way that whenever there is suspicious transactions, they will be rejected. Also, you are obliged to have this viewing key that you will need to show and audit, and maybe for some checks that these transactions actually are not are valid and are not somehow breaking the system.
Thank you.
One more question. Hi, thank you for presentation. I have actually two questions. One question is, you mentioned this AMM with kind of private and public, where the price change is public and the details of swap are not. But if the price changes, can I deduct what are the changes in the reserves? So basically, I know what was the swap.
I mean, you can know what happened. Like you can know that there was a change, but you won't be able to link it to this address or to this person, to this user.
Okay. And the other one, the users have to keep the proofs, right?
Sorry?
Users generate the proofs, and they are required to keep them safe, right? So if user loses their proofs, they basically lose the money that was locked, right?
I'm not sure about this, if the user lose the proofs. Actually, the users are proving that they have consumed some nodes or they have built some nodes. And what is happening is that on the public state, these funds are locked. So even if they lose this proof and they don't submit it, there is nothing that will be done. So the funds will be locked.
They cannot be unlocked. They
Sorry?
cannot be unlocked, right?
Sorry?
They cannot be unlocked. Only the only unlock is when you make this private transfer later. And to make this private transfer later, I need this proof to show that I'm spending the money that was locked.
Yes.
And if I lose this proof, it means that I lost this money that was locked, right? Kind of like if I lose my private key.
If you lose your private, yes, sure.
Okay, same situation.
Yes, sure.
Okay, thank you.
Sorry, we have to.
Just a
short
one.
Short one. Okay. How this functionality relates to the other products in the full portfolio, like Codex or Nomos?
Actually, for Codex, we don't have any link to it yet. But for Nomos, Nomos is working on zones. So Nescience can be a sovereign zone where they will generate the proofs, and then they will rerun our proofs and make us bridge with other nodes for now, until it's clear how the native zone in Nomos will be built. And I think that we might be able also to be a native zone within Nomos.
Thank you.
Thank you.